This topic is systems of equations, and I'll be very honest, the concepts here are straightforward. The lecture will be relatively short. Systems of equations are honestly the type of thing that it's best to learn by simply practicing a lot. And so we'll do some practice in class. You'll have some practice on the quiz, but I strongly encourage you to take advantage of the practice problems this week regarding systems of equations. So formally, a system of equation is any group of equations that is simultaneously true, which allows you to combine the equations together and then solve for multiple variables. There are many different types of systems of equations. In order to have solutions for all of your variables, you must have at least as many unique equations as you have unknowns. What do I mean by unique? For example, if you had the line 2x equals 5 and another line that said 4x equals 10, the second equation is actually just the first equation multiplied by 2. And so it's the same line, it's not a unique equation. So you cannot have any equations that are simply multiples of one another. And similarly, you cannot have any lines that are parallel to each other in all of the different dimensions simultaneously. So if you think about, what happens under these other scenarios? What if we don't have the same number of equations as unknowns? If you have more unknowns than you have equations, you're not going to be able to solve the system. You will end up with an expression for some of your variables, but they will always be in terms of other variables. If you have more equations than unknowns, you have a solution that's overspecified. There are many, many methods for solving that type of system. Regression analysis is one of them, where you have thousands and thousands of observations and you're trying to fit a few variables to those thousands of observations. Talking about that kind of stuff is beyond the scope for this class. So we'll be focusing in on systems of equations where you have the same number of equations as you have unknowns. There are really two different methods for combining equations in a system together. The first is combination through addition, and the basic concept is that if you add the two left-hand sides of the equation to the two right-hand sides of the equation, basically because the two sides of any equation are equal to one another, it's like you've added 5 to both sides of the equation. You're allowed to do that algebraically. So what we do is we first, before we perform the addition, multiply the first equation by negative the coefficient on x in the second over the coefficient on the first. And if you think through what that would mean, what happens is that the coefficient on x in the first equation becomes negative a2, so that when you add those two equations together, your x terms cancel out and you're left with an expression that only has y's in it, so you can then solve for the y's. Once you have a solution for the y's, you can then take your y equals some number, call it d, and plug d in for y in either one of your equations. It doesn't matter which one you use, and then solve for x. And then you will have solutions for both of your variables in a two-equation system. The second method is through substitution. Substitution is basically where you solve either equation, it doesn't matter which one, for either variable. Again, it doesn't matter which one, just look at them and figure out which one you think will be easiest. Once you've solved, you get an expression that says, say, x equals something in terms of a1, b1, y, and c1. You would then take that x and plug it into the other equation in place of the x. Next, you would have then that second equation just in terms of y. You would solve for the y. You would get some expression, y equals a constant d. And you'd go back and you'd plug in that value into either of the original equations and solve for the other variable, say x in this case. So let's do some examples. So here we have a system of equations, and I'm going to go ahead and solve it using both the addition and the substitution method. So to start off with, I'm going to look at these two equations, and I'm going to say, well, if I multiplied this second equation by 8, then these first two terms would cancel out. So I'll write the first equation completely unchanged, and then I will write the second equation having multiplied every term in the equation by 8. And here I'm just going to write 19 times 8. And we'll come back to that in a minute. So what I'm going to do now is add these two equations together. So my 8x minus 8x is equal to 0. I have 56y minus 3y. So that would be 53y is equal to 7 plus 19 times 8. And if you go ahead and do the multiplication out, you get that 53y is equal to 159. And then you divide both sides by 53. You get that y is equal to 3. So that's my first step. I have that y is equal to 3. I'm now going to plug it back in. It does not matter which equation I'm going to use. So I'll go ahead and do it into the first one. I say 8x minus 3 times 3 is 9 is equal to 7. So I move the 9 to the other side. I get 8x is equal to 16, or x is equal to 2. And I'm done. So let's see that same system of equations, but using the substitution method instead. For the substitution method, remember that the goal is to get one of the variables by itself. So I look at the second equation and I say, well, the x is pretty close to by itself right now. So I'm going to go ahead and multiply both sides by -1. And then move the 7y to the other side so that I get that x is equal to 7y minus 19. And then I'm going to substitute this entire expression into my first equation so that I get that 8 times 7y minus 19 minus 3y is equal to 7. You can see what I mean by the algebra sometimes gets a little bit tortuous. You get 56y minus, and I'm not going to multiply it out yet, 8 times 19 minus 3y is equal to 7. This may start to feel a little familiar to you. So now we have 56y minus 3y. We have 53y is equal to, I multiply these together, but I move them to the other side, so it's 7 plus the result. I get 159, and now I divide both sides by 53. I get that y is equal to 3. From there, the solution is exactly the same. This time I'll plug it into the bottom equation rather than the top equation. So I get that negative x plus 7 times 3 is 21 is equal to 19, so that I get that x is equal to 2. So here we have another system of equations to solve. But as you look at these equations, you might notice something unfortunate about the system. This system is in fact not sufficient to get correct solutions or complete solutions for x and y. And the reason is that the second equation is simply a multiple of the first equation. So if you multiply each of these terms by 2, you get the second expression. Now you might have seen that immediately, which is great, but I want to show you what would happen if you tried to use one or the other approaches to solving this system, if you didn't realize that these two equations were not unique. So to start off with the addition equation, what you would do is you'd say, well, I have 16x here, I want to cancel it, so I need to multiply this top equation by -2. So I would get negative 16x plus 6y is equal to negative 14. And then if you added them together, you would get 0 plus 0 equals 0, which just isn't that exciting and doesn't tell you anything. If you tried to do this by substitution, it would just take you a little bit longer to get to the same conclusion. So if you said, well, let's try and get x by itself, we would get that x is equal to 1/8 times 7 plus 3y. I'd go ahead and plug that into the second equation. I would have 16/8 times 7 plus 3y minus 6y is equal to 14. So there I just took this x expression and I plugged it into the second equation for x. If I then multiply it through, this is equal to 2, so I get 14 plus 6y minus 6y equals 14, or I get the exciting expression that 14 is equal to 14. No kidding. So if you ever get one of those weird results without seeing in advance that you have a problem, that's what it's telling you. It's telling you that one of your equations is simply a duplicate of another of your equations. So now let's look at this more complicated system of equations. Unfortunately, when you add another equation and another variable, that simply makes for more algebra. Whether you use the substitution or the addition method is very much up to your personal preference, but I will argue to you that there are some situations where it's faster to do one and other situations where it is faster to do another. So for example, I look at the first and the third equations here and I realize that if I add them together, the y's and the z's will cancel out. So if I took x plus y plus z equals 6 and x minus y minus z equals 0, and I add them together, I get that 2x is equal to 6 or x is equal to 3. It's fine if you don't see that right away. This is one of those things that comes with practice, but if you do see something like that, definitely take advantage of it. So now I'm going to rewrite these equations in terms of just y and z. So I have that y plus z is equal to 3. What I did is I said x is equal to 3. I moved it to the other side, so that's 6 minus 3. 3x is equal to 9, and so that's going to cancel out the 9 over here. So what that tells me is that negative 2y plus 4z is equal to 0. So now that I have these two equations, two unknowns, I can substitute or I can add. It doesn't matter. For me, I look at this first equation and I say that's pretty easy to get y by itself. So I'm going to say that y is equal to 3 minus z. And then I'm going to substitute 3 minus z in for the y here. So I get negative 2 times 3 minus z plus 4z is equal to 0. Negative 6 plus 2z plus 4z is equal to 0. I move the 6 to the other side. I get that 6z is equal to 6 and that z is equal to 1. Now realize that any of the intermediate equations that you've used actually is still a true statement. So I can say, you know what, I've already solved this first equation for y. I'm going to take advantage of that algebra that I already did. I'm just going to plug this z is equal to 1 back into that equation that I had. So I get that y is equal to 3 minus 1 is equal to 2. So my solutions here are that x is equal to 3, z is equal to 1, and y is equal to 2. In some ways, systems of equations are the one thing that you'll see from this class in almost every class you're going to take, and certainly in economics it's going to appear fairly frequently. So I thought I'd do a few examples that grow out of market equilibrium. You very often will see an equation. This first equation here is for the demand curve. So this is the price on the demand curve is equal to a constant 400 minus 2 times the quantity demanded. And on the supply curve, the price is equal to 100 plus the quantity that's supplied. Now you might look at these two equations and say, oh no, I have two equations but four unknowns. And this is where you add basically two equations to this system, and we almost never write them out because it's a little silly to write them out. If we have market equilibrium, it means that the price demanded is equal to the price supplied, and that the quantity demanded is equal to the quantity supplied. So if what you're solving for is the market equilibrium, usually what people will do is just write that in terms of the price and the quantity, and you can then rewrite your demand equation as price equals 400 minus 2 times quantity, and your supply equation is equal to price equals 100 plus quantity. Notice that these equations, these are not the equations for the line. These are the system of equations is the system describing the market equilibrium. Another way of saying that is that's just the intersection of this demand curve with the supply curve. Even better, when you get these equations, they're almost always solved for the price or the quantity, usually the price. And so what you can do is you can just set them equal to one another. So you get 400 minus 2q is equal to 100 plus q. I move the 100 to the other side, I get 300. I move the 2q to the other side, I get 3q, and I solve and I get that the quantity demanded in this market equilibrium is 100, and then I can plug that 100 back in. I'll use the second equation and notice that the price is equal to 100 plus 100 or 200, and so my solution is that price equals 200 and quantity equals 100.